Welcome back to Algorithmic Game Theory. This will be our final lecture today. Thank you very much for staying this long. Today we'll be discussing a topic which you could also call fair division, but usually it goes by the name cost sharing. What's the general problem? Well, suppose you and your friends want to buy a train ticket. Now you can save money, all of you together, if you buy a group ticket rather than buying all individual tickets. However, the question will be, how do you split up the cost among all your friends so that everybody feels treated fairly? There are different ways of defining this, some of which have some advantages, others have other advantages. And today we'll see two different approaches of how to split cost and what properties they fulfill. So let's first define a model. We have again n agents, which we again call capital N, and we have a cost function. That is just one cost function which maps from all subsets of the agents to a real number. So CFS, this is the cost that S would have on their own. And we'll assume that for the empty set, this is 0, but for others, the cost can in principle also be negative. So what might that be? We might have a train ticket and we might have 5 agents. Then a single ticket will be €5. A single ticket will be €2, and a group ticket will be €5. So what would that mean? The cost of a set of agents will be the minimum of 2 times the number of agents in that set and 5. So if it is just 2 people who choose to buy a ticket, then they'll have a cost of 4. If there's only 1 person who wants to buy a ticket, it will be a cost of only 2. But 3 or more agents, they immediately have a cost of 5, because they together can buy a group ticket. So what will now be our question? Our question will be to split up the cost that we have for the entire group of people. So CFN we want to split up among all agents in N, so that the cost, of course, will be covered, the overall cost will be covered, and each of the agents is treated in a fair way. So more formally, our goal will be to find a cost-sharing vector psi of c, which of course depends on the cost function, which now splits up the cost among all n agents and when all agents together, they exactly cover the cost. Well, clearly there are different ways of defining such a cost vector. In our example here, how could this look like? We could, for example, say the first two agents each pay 2 euros, the next agent pays 1 euro. Or the first agent pays all 5 euros and the other agents pay nothing. Or each of the agents pays 1 euro. Some of these we might consider more appropriate than others, and this is exactly the question that we're asking today. What is it that makes such a cost-sharing vector fair or appropriate in any possible sense? The first way of choosing such a cost vector, a cost-sharing vector, I'd like to discuss now is the so-called core. For a cost-sharing vector to be in the core, several properties, namely 2, have to be fulfilled. And these are the following. We say that psi of c is in the core of C if it fulfills on the one hand, it should fulfill a property called efficiency, which we've already seen, the sum of the individual cost shares should sum up to 1. The sum of the individual cost shares should sum up to the cost of all agents together. So the sum of the individual costs exactly recover the social cost. And then we also have stability, which means the following, that the sum of the cost shares is no more than the cost of a set for any sets of agents. So no coalition pays more by this cost-sharing vector than they would if they just did their own thing and just, for example, bought a train ticket just for this group of people. Is there a core outcome in our train ticket example? Yes, there is. So we had CFS to be the minimum of 2 times the cardinality of S and 5. Now, what might be a core outcome? We might, for example, set Ci and psi I of C equal to 1 for all I. This will be in the core. Or we might, for example, split up the cost that the first 2 agents pay 2, the next agent pays 1, and the remaining 2 agents pay nothing. This is also in the core. But having, for example, the first agent pay 3, the second agent pay 2, and the remaining agents pay nothing, this will not be in the core. Why that? Because the first agent might decide to just buy a train ticket only for themselves. And then this agent will pay only €2 because that was the price for a single train ticket. But here we are saying, okay, you'll have to pay 3. Or also for the first 2 agents, they could also say, our cost together is only 4. So C of the set 1 and 2 is 4. But here together we'll have to pay 5. Good. So while generally this first feels a little better than the second, I think this core already captures quite some properties that we would want to see fulfill in cost sharing. Unfortunately, there is not always a cost sharing vector in the core. Sometimes the core can be empty. When would that be? We could, for example, have 3 agents and the cost for a set of agents would be the cardinality of that set divided by 2 rounded up. So this maybe looks much more fancy than it is supposed to be. This cost function is 0, of course, for the empty set. For sets of cardinality 1 or 2, it will be 1. And for the set of all agents, of all 3 agents, it will be 2. So in the language of train tickets, we can understand this like there being only group tickets for groups of up to 2 people. Now, if 2 agents buy a ticket, they pay 1 for 1 ticket, but if all 3 agents want to buy a ticket, they have to buy 2 tickets. In principle, they could also take a 4th person, but there is no 4th person. And I claim now there is no cost-sharing vector that is in the core. Why is that? For psi of c to be in the core, we would need that the cost is covered, the cost that all 3 agents have together is covered. The cost of the first and the second agent together, well, they shouldn't want to buy just a ticket only for themselves, so this shouldn't be more than 1. And that holds for any pair of agents, so also for the first and the third agent. And also for the second and the third agent. And if you add up all these inequalities, then you'll see, okay, 2 times psi 1 of C plus 2 times psi 2 of C plus 2 times psi 3 of C. That'll be at most 3. And this is certainly a contradiction. So this core, this is a nice idea, and sometimes there is indeed such a cost-sharing vector, sometimes there isn't, unfortunately. Of course, you might now ask the question, when is there a vector, a cost-sharing vector in the core? So under what conditions is the core not empty? But we won't be discussing this question today or in this class, but we will rather move to a different way of sharing the costs now. Now we'll talk about the Shapley value, which is a different way of finding a cost-sharing vector, which fulfills a set of properties. And indeed, as we will show, not only does it fulfill the properties, but it is also the unique choice of a cost-sharing vector that fulfills these properties. So what are these? We are talking about symmetry. If we now take two agents, and let's consider any other set of agents for which neither I nor j is contained. And if now the cost after adding I will be exactly the same as the cost after adding j, then the cost share should be the same. So this is somehow representing what we, for example, see in the example of these train tickets, that there all agents are actually exactly the same. So why should they pay any different amounts? And this we can formalize in the following way. So if two agents have the property that if we add them to any set that we might add them to, which contains neither of them before, then always the cost will be the same regardless of which of the two we add, then they should pay the same. There's another property, which is the so-called dummy property. If for an agent, for all sets of agents, the cost of adding that agent is equal to 0, meaning that the cost after having added this agent is exactly the cost that we had before adding that agent, then this agent should not be paying anything. This is also a very natural property, but it is hard to come up with an example in reality. For example, if kids ride for free on the train, then and under all circumstances, even if they are alone, they don't pay anything, then why should they get associated some cost share in our cost sharing vector? This is the dummy property. Now, one further property that we've seen a number of times, we want the cost sharing vector to be efficient. So it should sum up to exactly the cost that all agents have together. And finally, our third property, if we take two cost functions c and c prime, we should have that the cost that we associate to agent I when we are splitting up the cost of c plus c prime, this should be exactly equal to the cost that we're assigning to agent I when we split up c and what we assign them when we split up c prime. And so here this is the pointwise sum, meaning that c plus c prime of s is nothing but c of s plus c prime of s. So in other words, this additivity asks us to split up the cost so that if we buy, say, train tickets and theater tickets, then we should split up the cost exactly the same way as if we were only splitting up the cost of train tickets, plus if we were only splitting up the cost of the theater tickets. This also feels very reasonable. So, is there a way to always fulfill these properties? Yes, fortunately there is. And not only this, there is even a unique way. But before we come to this uniqueness, let's first see how we can fulfill all these properties. And to do this, what we'll do is we'll first define an auxiliary function. Namely, let's take any permutation pi of the agents, and now we'll say phi of c comma pi will be equal to the following. Take agents that are the first k in the order of the permutation, and from that subtract, so take their cost and from that subtract the cost if agent k was not included, agent pi of k, and this I want to do where k is equal to the inverse of the permutation of I. This looks very fancy, but it is actually something super easy. Namely, we now take any permutation of the agents. Maybe for starters, let's just think of the identity permutation. So agent 1 will be at position 1, agent 2 will be at position 2, and so on. And now we'll take the cost of agents 1 through I, And from that, we subtract the cost of agents 1 through I minus 1. So this will then be the marginal cost, so the cost increase that we incur by including agent I. And we'll consider this for any possible permutation. So rather than just going through the agents in order 1, 2, 3, and so on, we might also consider them in order 5, 4, 3, 2, 1, or whatever. So seeing this again in more details with concrete numbers, let's recall our example of the cost-sharing function, which was 2 times the minimum of 2 times the cardinality of the set and 5. Now if we have pi of I equal to I, then we have that phi of 1, c, pi will be same as phi of 2 of c, pi, namely 2. The first two agents that we add, they will cost 2. The third agent, they will still cost 1, and the fourth and the fifth agent, they won't cost anything. Well, clearly this does not fulfill our symmetry condition, because now these agents, which were initially all the same, those now have to pay different amounts. But this is exactly what the permutation is for, because now we could also alternatively consider them in order 5, 4, 3, 2, 1. And then suddenly agents 4 and 5 would have a cost of 2, agent 3 would again have a cost of 1, and agents 1 and 2 then would have a cost share of 0. And the point of the Shapley value is just to try out all possible permutations and just take the average of all these functions over all possible permutations. And by this, we will then also ensure that this symmetry condition is fulfilled. So we will define agent I's Shapley value under cost function C as psi of C is equal to 1 over n factorial times the sum of all permutations phi of C, pi. And here we mean by Sn the set of all permutations on n. So in particular, the cardinality of this will be n factorial. Good. Now I claim that the cost vector that we defined this way fulfills all these properties that we were naming, namely symmetry, dummy, efficiency, and additivity. So psi of c defined by star fulfills symmetry dummy efficiency and additivity. Is this surprising? Most of this is not really surprising, because these phi vectors, they actually fulfill almost all of this, namely they already fulfill dummy efficiency and additivity. Only they do not fulfill this symmetry. So if you now wanted to verify this, for example, this dummy condition, let's once again have a very quick look at this. What would happen here? Dummy, what was that? No matter which set of agents you add this agent to, this will never change the cost. And this means that for any possible permutation, this here will be exactly equal to this here, because if pi of k is in the set or not, this doesn't make any difference. So this is why this already fulfills this dummy condition, and if we now just take an average over these functions, this still maintains the dummy condition. A little more interesting is maybe the symmetry condition, because it is not fulfilled by the phi functions. So let's have a closer look at why this is now suddenly fulfilled. And of course, the reason is that we are taking the average over all permutations. So for symmetry, consider two agents I and j such that CFS union I will be equal to CFS union j for all S with I and j not in S. Now we will define for any permutation pi, there is exactly one permutation, pi superscript I comma j, with the following: I and j are simply swapped. Namely, what used to be pi of j is now pi of I, and vice versa. So we'll swap the images of I and j, and everything else we just don't change at all. And what will happen now? This phi of c comma pi, this is for agent I, so phi I of c comma pi, this is exactly equal to phi j of c comma pi pi superscript I comma j. And this means that the cost share for agent j, which we can write as also the average of these phi functions, but now taking, instead of the permutations where we swapped I and j, well, then we'll get exactly to the same that we were getting to if we considered agent I without swapping I and j. And so this implies that psi of I and psi of j will be equal. So what is important here is that it doesn't actually matter whether we take the sum over all possible pi or the sum over all pi superscript ij, because these permutations pi and pi ij, they are just in one-to-one correspondence. For each permutation pi, there is the respective permutation pi superscript ij and vice versa. So this is why we can actually also here just take this sum over all pi, but still take here the pi superscript ij. And then here what we see is what this ij does is it is actually just swapping the roles of I and j, and this is how we then end up that I and j have to be getting the same. And as I was saying, for the other conditions, we can immediately use the fact that also already these phi functions fulfill them. Let's maybe just see this very quickly, why this is also true. So we were already talking about dummy, which is extremely boring. This is the thing I mentioned before. Namely, we'll have that this will be 0 for any agent I with the property that adding him or not does not change the cost. And so we'll also have that the cost share, which is nothing but the average of all these phi values, this will have to be 0. Analogously, you can do this also for efficiency and for additivity, because also there you show this for these phi functions that this is fulfilled. And this is nothing but, well, following the calculations. And then you again take the average of these phis, and then you again get to the point that everything works out. And so for additivity and efficiency, I just want to ask you to have a look at the lecture notes. Good. So now we found a way of sharing the costs which fulfills all these nice properties, which felt very reasonable. This might be a core outcome, but maybe it is not, because the core might be empty. But to what extent do we still have a freedom? We now found this way of defining the Shapley value, but could we have done it in a different way? The point is, no, we could not. The way of defining the Shapley value, this is actually the unique way that all of these properties are fulfilled. And this is still remaining for us to be proved. This is the way of how we define the Shapley value. And we've now verified that it fulfills all these conditions that we were requiring. But are there other cost-sharing vectors that fulfill all these properties? No, there aren't. Well, so while for the core we might have multiple or no cost-sharing vectors, here this is actually the only way of how we can choose this cost-sharing vector. So this psi of c defined by the star are the only vectors that fulfill symmetry, dummy, efficiency, and the additivity condition. How do we prove such a claim? Well, we will now consider different cost functions, and due to additivity, for example, every general cost function can be expressed as a sum of these cost functions that we will be considering, and then we will for such a function derive using symmetry, dummy, and efficiency that for such a function the way of setting the values is unique. And let's start this with the following lemma. Let's consider a set T of agents, and for that let Ct be the cost function such that C of S will be 1 if S is a superset of T and 0 otherwise. This might not be the most intuitive cost function because now every set of agents costs nothing unless it contains the set S. So the set T. So speaking of these train tickets, this is maybe not what you're envisioning, that groups of 5 people are for free, but 6 people suddenly they cost 1. And even worse than this particular group of 6 people, they cost 1, But if only one of them stays at home, they don't pay anything. Good. But for these kinds of functions, we can now show the following. Then for any fixed alpha and t, the unique psi of alpha times ct that fulfills the symmetry, dummy, and efficiency condition is the following. Psi I of alpha times ct will be equal to alpha over the size of t if I is in the set t and 0 otherwise. What do I mean by this notation? I just mean that this function ct we multiply by any alpha, and that should be just any real number. So rather than having this function ct of s, we now just take alpha times ct of s, which just changes this to alpha. And we now claim that for this function, this kind of a function, the way of sharing the costs, fulfilling symmetry, dummy, and efficiency condition, this is unique. This has to namely be this way. Why that? Okay, that's actually not so difficult to see, because there's actually only two ways an agent can influence the cost vector, namely it is either in the set T or it isn't. And what happens if I is not in T? Well, then we'll certainly have that Ct of S union I will always be Ct of S alone for all S, because all that matters is, does this S contain all of T or doesn't it? And this is true if I is not in T, then suddenly this does not make a difference. So this means that psi I of alpha times Ct will have to be 0 by the dummy condition. So the only point is that an agent that does not belong to the set T, this cost function doesn't really care about. So by our dummy condition, it should get a cost share of 0. Now by efficiency, what else do we have? We will have to have that the sum of all agents' cost shares will have to sum up to alpha, because what's the cost of all agents together? All agents together, they certainly contain the set t, so that will be 1, and so here we'll have alpha of t, so alpha times 1, so they will certainly have to pay, or the cost of all agents together will be alpha. Now what we see here is that this will be equal to the cost share, the sum of the cost shares of only the agents in T, because all other agents don't pay anything, as we have already derived. Now by symmetry, for any two agents I and j, we will have to in T, we will have to have that psi I of alpha times Ct will have to be equal to psi I of alpha times Ct, psi j of alpha times Ct, which means, combining this, that psi I of alpha times Ct will have to be alpha divided by the cardinality of T for all I in T. So nothing spectacular is actually happening here. There's the group of people who are not in T, and for those, well, they don't make any influence, so by our dummy condition, the cost share will have to be 0. For the ones who are in T, they have to all pay the same. And together they have to pay alpha, so the point is they all have to pay alpha divided by the size of T. Good. So for this kind of a function, alpha times Ct, we already have derived that the way of sharing the costs is unique. What we'll do now is we'll combine every cost function as just a sum of such alpha times Ct, and then by additivity we get to the point that, okay, the cost share of every agent is actually determined by the way we're splitting up things here. And how do we do that? We'll first show the following lemma. We'll show that for every cost function C, there is a unique choice of a sequence alpha t where all of these are real numbers, such that C can be written as the following: take the sum over all alpha t times Ct. Ct, those are again the functions for which the cost is 1 if all of t is contained and it is 0 otherwise. And now what we'll effectively do is we'll present C as a linear combination of these, or in other words, we just find a vector of these alpha t values such that the cost function is represented by taking a sum over all possible sets t, alpha t times Ct. And when we're done with this, we are almost there, because then, by what we've shown in the previous lemma and together with additivity, then we see, okay, the choice of the costs is unique. But let's first show that actually there are these unique choices of alpha t. It has to hold for all s that C of s is equal to, take the sum of all t that are a subset of n, t is not the empty set, alpha t times ct of s. Now what is this that we have here on the right hand side? Ct of s, I hope you remember, that was equal to 1 if s was a superset of t and 0 otherwise. So what we might here also just write is we could as well take the sum over all t, which are subsets of s, t shouldn't be the empty set, and then we just get alpha t. So what we're getting is that we have a system of linear equations. We'll have C of s will have to be equal to this. And how many variables and how many constraints do we have? We'll have two to the n minus 1 variables, namely all these alpha t, for t being a subset of n, but t is not the empty set, and we'll also have as many constraints, namely that we have the s, which are also a subset of n, and s shouldn't be the empty set, because for the empty set all this will be 0. So all we have to do is we'll have to see that this system of linear equations actually has a unique solution. Why is that? Well, the one way you can think about this is, what would these alpha values be for the singleton sets, for the sets that contain only one element? For these, they will have to be just exactly equal to the cost of that particular single agent. Because we'll have to have this here for S being just containing, for example, only element 5. We'll take here the sum over all t, which are a subset of this, but not the empty set, so this is exactly one set, namely that set, the set that contains only that agent. And then you see, okay, this here, this alpha s, will have to be equal to C of s for sets of cardinality 1. Now move on to sets of cardinality 2. For sets of cardinality 2, we see here actually everything is fixed by our argument. Every strict subset of S, we already know that this has to have a certain value. And then we think, okay, there's only one more available, and that is now also fixed because C of S will have to be equal to this alpha of S plus whatever we had to fix before. And this way, if you just go through this from the bottom up, you see, okay, there is actually no choice that you ever have. There are many ways to write this down formally. One way that I now like to write this down is as follows. We'll order the variables and constraints by increasing cardinality of T or cardinality of S, respectively. Breaking ties arbitrarily, of course. And what we'll see now is the following constraint matrix. We will have ones on the diagonal. Above the diagonal, we'll have zeros. And below the diagonal, I don't know, but I don't care. Why that? So this here, this will be the variables. And so we have them now for, this will be the increasing T. And here we'll have the constraints. And this will be about the sets S. Now what does this first line here say? This is about the set S that contains only one element. And for that we see, okay, here in this sum we'll see exactly one variable, namely the variable that corresponds to that set S, which contains only one element, and this means that in our constraint matrix we'll have exactly 1, 1 here. More generally speaking, for any of these rows, we'll have a 1 here on the diagonal because the respective constraint always includes the variable for t being equal to s. And then we'll have something here which we don't care about, but right off the diagonal, that would mean that t is bigger or at least the size of s. But if t is at least the size of s, but not equal to s, then this will not be part of this sum. This sum is definitely only including sets t, which are either equal to s or which have a strictly smaller cardinality. And this is why the constraint matrix will look like this. And if you now run the Gaussian algorithm, you will get a unique solution because all that you have to do is you only have to eliminate these question marks down here. And this shows that this system of linear equations always has a unique solution. Good. And now we come to the point that we combine these lemmas to show that there is always the way of splitting the costs is actually unique. Once again, this was our theorem. Our theorem said that there's only one way of splitting the costs that fulfills symmetry, dummy efficiency, and the additivity condition. And what we saw is that this already holds true for these CT or alpha times CT functions. And now we have that also every function can be uniquely expressed as a sum of these alpha times CT. So this immediately means that this psi function, that has to be unique. And what about now the point that it has to look like how we derived this before? It has to be the Shapley value? Well, we just verified that the Shapley value fulfills all these conditions. So just by uniqueness, this has to be the one. So let's complete the proof of our theorem. Namely, if we now let C being equal to alpha t times ct be the unique decomposition then by additivity we'll have that psi I of C will have to be equal to psi I of this sum that we have here. Now we can move the sum out of this psi. And this here, this will be equal to alpha t over cardinality of t if I is in T, or it will be 0 otherwise. So this will be nothing but the sum over all t with a property that I is contained in T alpha t over the cardinality of T. And because this vector alpha t was unique, this is unique. And this, of course, does not look at all like this Shapley value that we were defining, but it has to be the same just because we just proved uniqueness. And having proved uniqueness, how could this be any other way? Let's wrap up our discussion here. We've seen two ways of cost sharing today. One being the core, and there sometimes might be multiple vectors in the core. That by itself wouldn't be a big problem, but sometimes the core can also be empty, which is quite a bummer. Then we also got to know the Shapley value, and the Shapley value, of course, is always defined. And not only that, it is also the unique way of defining the cost share such that these natural axioms are fulfilled. An open question is, of course, under which conditions is the core not empty, and under which conditions is the Shapley value part of the core, an element in the core. This is something we unfortunately don't have time to discuss in this class, but still there's interesting research on this. You can also think of this in a more general sense, namely, you can ask, how can we more generally capture these kinds of settings? And indeed, this game that we have been considering today is a cooperative game with transferable utilities. And what is interesting to me is that you can also understand questions like as house allocation or stable matching. You can also interpret as a cooperative game, but then with non-transferable utilities. So in a way, we were somehow between mechanism design with and without money today, because we had these transferable utilities, yet still thinking about all of this with the perspective of mechanism design without money, at least the way I understand this. One final remark that I forgot to make earlier is it actually easy or difficult to compute the Shapley value? Unfortunately, it is not really easy. The way we stated it, this takes like time n factorial to compute. If you exploit more symmetries, then you get it down to 2 to the n. This is still not a running time that makes me happy, but it's at least doable. Yes, and this brings me to the end of these lecture videos. I hope you enjoyed watching them. As usual, if you have any questions, please do get back to me. And let's hope we see each other soon again. Stay safe. Bye.